All right, guys. So this third question is solid barium hydroxide is added to a solution of hydrochloric acid to produce aqueous barium chloride and water. The test tube feels warm. So this is the first one, I think, if I'm not mistaken, in this packet that has to deal with your polyatomics. So remembering that those polyatomics are still fair game on Unit 2 test. Again, everything from Unit 1 is still relevant and important for Unit 2. Now we're just putting it together in reactions and incorporating some moles and mole ratios. All right, so we've got sodium barium hydroxide. So in my periodic table, I'm aware that barium is going to be in the second column. So if I can find my periodic table here quickly, preferably quickly. All right, barium is in the second column with a charge of +2, and hydroxide is going to have a charge of -1. So you're going to have one barium hydroxide and one barium with 2 hydroxides, excuse me. All right, so that is added to a solution of hydrochloric acid and aqueous barium chloride. So we know that this is a solid, we know that this is aqueous because all acids are aqueous, and we get barium chloride. Chloride has a charge of -1, barium has a charge again of +2, so same thing, we have 1 Ba for 2 Cls plus some water left over. This is aqueous, this is liquid. The other thing that we know is that the test tube feels warm. And what we know when the test tube feels warm is that thermal energy was released. And so we need to add energy on that product side of the reaction. Okay, so next up I have to go to balancing. So balancing always happens, again, after we create the completed proper molecule equation, because if we didn't have that, we wouldn't be getting anywhere. So we look, and the first thing I see is that, let's see, I see I have 2 chlorines here. So I'm going to balance that and make sure that my chlorines match. So now I have 2 chlorines in both places. The next thing that becomes a little bit wonky is checking out my oxygen. Oxygen is always a tough one. So on this side, I have 2 oxygen. On this side, I have 1 oxygen. So I know I'm going to need to add a 2 there. That 2 is going to change my hydrogen. So now I have the right amount of oxygens, but I need to double check my hydrogen just in case. A very common mistake in these sorts of problems is to say, all right, well, I have my 2 H's. Oh no, that's all I have. That doesn't match with my 4 on this side. And so you start making things real complicated, but you have to remember to look on both molecules. So I have 2 hydrogens here, but also 2 hydrogens there, which give me my 4 hydrogens. And that means that my reaction's balanced. So just be very careful that you're looking at all of the locations where these particular atoms are showing up. Okay, so what exactly is happening here? Well, barium is switching places with hydrogen, and chlorine is switching places with the OH. So my anions over here, or excuse me, my cations over here are going to switch place with their anion partners. So barium is going to tag team up with chlorine, and OH is going to tag team up with H to give me water. So it's a double replacement reaction. Okay, so now let's do the energy bar charts. So thinking about what happened here and what I know. So I always like to start with the what I know. And what I know is that the test tube feels warm, which means that energy is a product of this reaction. All right, so the warmth of the test tube indicates that energy is leaving the system. If I start with 2 bars of energy, because that's just what I start with, then I have to think about what's happening in order to get 1 bar of energy to leave, observing the fact that I can't create or destroy energy. So what has to be happening? Well, chemical energy has to be converted into thermal energy. That's the only places I have energy, which means that the only opportunities I have is that thermal is going to chemical or chemical is going to thermal, because I'm not inputting anything into the system. It would have to say something like overheat or heating or something, over fire, over flame, that shows me that it is consistently that energy is consistently flowing into the reaction. In this case, since nothing is going into the system, I know chemical energy must be converting to thermal energy, which is going to give me 3 bars of thermal energy to 1 bar of chemical energy. Okay, and then because we have to start and end at the same thermal, because room temperature, or whatever given temperature it is, we have to start and end in the same place, so my chemical energy still stays at 1 bar, my thermal energy goes back to 2 bars, and 1 bar is released into the atmosphere. Again, what you should be able to do if you're sticking with the number of bars, I have 4 bars, no bars are entering the system, which means I need to end up with 4 bars, and at the end I need to account for 4 bars. 1, 2, 3, 4. All of the energy needs to be accounted for. So that's the balancing and the energy. If we're doing an energy curve, what's happening with chemical energy? Well, it started at 2 bars and it ended at 1 bar at the end of the reaction. So it started up here. As the reaction progressed, it lost energy, and where it ends is at that 1 bar. Okay, so my reactants are up top. My products are down here. The amount of chemical energy decreased. Okay, so now let's transition to some mole problems. 56 grams of barium hydroxide is how many moles of barium hydroxide? This is pretty simple, right? 56 grams of BaOH2. Now, a couple of things that people mess up on is that they say oxygen is 16, hydrogen is 1. So my oxygen is worth 16, my hydrogen is 1, and my barium is, let's check over here, my barium is 133.3. Okay, and then zooming, 133.3. But keep in mind that 2 is distributed, so this is 16 times 2, 1 times 2, and 133. That's going to give us a total of 171.3 grams of barium hydroxide in 1 mole. So again, I need to get grams on the bottom. I need to do that so that the units cancel out, and that equates to 1 mole of BaOH2. If you're keeping track of the units, grams barium hydroxide cancel, grams barium hydroxide cancel. What am I left with? I'm left with 0.327 moles of BaOH2. All right. Now, remembering again that we cannot do anything in grams. We cannot compare any molecules, any atoms, any masses. We can't compare any ratios. This ratio, again, up here has nothing to do with grams. You have to convert to moles. It's the standard communicative system. We cannot compare grams because everything weighs something else, so they just simply don't equate. So I'm going from barium hydroxide over to barium chloride, completely different atoms, completely different masses. If I'm trying to figure out mass, I have to have some sort of standard number of molecules that I'm talking about. And again, that's where the moles come in. So I come down here to how many molecules of barium hydroxide would this be? And this is what I was getting at. You're taking a certain amount of molecules of barium hydroxide. You could have the exact same number of molecules of barium chloride, but the masses would be distinctly different because of the atom and the molecule structure. So if I come back over here, if I have 0.327 moles of barium hydroxide, again, everything's a ratio. You just need to figure out which ratio you're using. In this case, I'm using the literal mole ratio, where 1 mole is absolutely always a certain number of molecules. So in this point, 6.02 times 10 to the 23rd molecules of BaOH2. That just got me out of moles, and now I'm in molecules for a total number of 2.79 times 10 to the 17th molecules of BaOH2. So if you guys want to sit here and complain about moles, it's a heck of a lot easier to say 0.327 moles of something than it is to go out there and count 2.79 times 10 to the 17th molecules of something. So just keep that in mind in terms of when we're frustrated about our good old-fashioned handy-dandy moles. So then it says how many moles of each product are produced. So if I come up here and I say, well, nothing new has happened. We don't need to start making up numbers. it says how many moles of each product based on 56 grams of barium. So what I know is my moles of barium. You can't go backwards and start using grams again. You need to understand that these two things are the same thing, except moles are the universal language. So how many moles of each product are produced? This is where the mole ratio comes in. So if I start with 0.327 moles of BaOH2 for both things. So I just learned this new handy dandy little, I didn't just learn it, it's not that bad. But I did learn it relatively recently. Okay, so there we go. So I have 0.327 moles barium hydroxide. And I need to figure out the number of moles of each of my products it's going to make. So it's going to make two products. Why'd I go to black? It's going to make BaCl2 and it's going to make H2O. But as you can see, my mole ratio of BaOH2 is 1:1 when it comes to BaCl2, but it's 1:2 when it comes to water. This is why moles matter. So I know that for every 1 mole of BaOH2, I'm going to make 1 mole of BaCl2, which I know, really advanced arithmetic here, 0.327 moles of BaCl2. Again, you can keep track of everything. I know it seems obnoxious, but everything needs to cancel. You need to be left with one set of units and one set of molecules. So that's easy enough. Now I come down here and I figure out how many moles of water are going to be made. So I start with 1 mole of BaOH2 will give me 2 moles of H2O. Again, coming back up here to my mole ratio, where 1 BH2 is going to give me 2 H2O molecules. All right, so the ratio here changes. And what does that mean? What else does that mean changes? The number of those molecules that are going to be produced. So now I'm going to, in the same reaction with my same starting moles of barium hydroxide, I'm actually going to produce 0.654 moles of water. Okay, because again, it's not saying anything about mass. It's not saying anything about that. It's saying I have this many molecules of this, and it's going to react with this many molecules of this, and it's going to produce this many molecules of this and this in a very strategic and specific ratio. However, we don't use molecules because they're so small. So that's why we have to use moles. The way that a mole and a molecule works is the same in terms of the ratio, and that's super, super important. That's why you have to be in moles. The only time you should be converting into and out of grams is at the beginning of and at the end. Nothing you do in the meat of the reaction or in the meat of the math is ever going to have to do with grams. That's simply a conversion tool for you to get from grams to moles. From mass, which is arbitrary, to moles, which I can have a very clear understanding of exactly what a mole is. So I hope this problem was helpful. I will upload question number 4 here momentarily.